Hey guys, welcome back to Quick Code. Today we're doing another Brainstellar Quant puzzle. This one is called Messing with Envelopes. It's another hard problem. I'll let you guys pause and go over the problem once. So first of all, let's try to understand the problem. So we've been given n letters, where n can be any number. We've just taken n as a general value. So for example, let's say n is equal to 5. So we have 5 letters, and each one of those letters are numbered. So let's just denote them by numbers from now onwards. And we've also been given n envelopes, right? So we'll just call them slots for now. So we've been given, so for n is equal to 5, we have 5 numbers and 5 slots. And what's happening in the problem is, well, for each number, its corresponding slot was the same value. So for number 1, it was supposed to go into envelope or slot number 1. Similarly for 2, 3, 4, and 5. And for every number, right? Because that slot is the corresponding place for this number, the correct place for this number. But what happens is, for each number, we now randomly assign it any one of these slots, right? And this happens for each number. So each of these numbers is assigned any random slot. Now what happens is, because of this, so the correct permutation was 1, 2, 3, 4, 5, 6, and so on, denoting that the number 1 was placed at the first slot, the number 2 was placed at the second slot, and so on. But what happens is, because each of these numbers is assigned a random envelope, a random slot, we get a random permutation of these n numbers. So an example for n is equal to 5 could look like 3, 1, 4, 5, 2. Right? This denotes that the third envelope got slot number 1, the first envelope got slot number 2, the fourth got slot number 3, fifth got this fourth slot, and the second number went all the way to the fifth slot. So over here, as we can see, since there is no number which is at its correct position, the number of matches. So now we're going to also introduce another term, matches. Matches just mean that there's a correct matching of the number and the slot, right? So since there's no number that is in its correct slot in this permutation, there are 0 matches. For example, let's take another permutation. So 1, 2, 4, 5, 3. So over here, 1 and 2 are in its correct positions, right? And 4, 5, 3 aren't. So over here, the number of matches is equal to 2. So according to the question, so what we're expected to find out in this problem is the expected number of envelopes with the correct letter inside them, or basically this just means a match. So what we're trying to calculate is, given a random permutation of n numbers, right, where n is any general number, what are the expected number of correct matches that are gonna happen? So coming towards the hints now, well, one very common trick that we've used a lot in probability and Brainstellar problems in general is recursion. Now, how did I come up with using recursion? Well, since the question states that there are n values or n letters and envelopes, I started with n equals to 1, 2, and 3, and so on, because these are simple base cases, these are simple cases, and it's always beneficial to try out simpler values, right? And I started to see a pattern between each of the values. So for the case of n, I could somehow figure out that it's dependent on n minus 1, the state of n minus 1, and n minus 1 was in turn dependent on the state n minus 2. And this led me to the idea of using recursion. So first of all, let's start off. So let's just take a variable k, and for, let's say, k is equal to 1, or basically we're saying n is equal to 1, right? So for one number and one envelope, what's the expected number of matches that we're gonna get? And we're gonna denote that by e of k. So e of k is the expected number of matches that we are gonna get given we take the case of k letters and envelopes. So for e of 1, well, we see that this number is always going to be assigned this slot over here, right? Because there's no other slot. So, and whenever this number 1 is going to be assigned slot number 1, it's going to lead to a match. So e of 1 is equals to 1, right? And now if we look at k is equal to 2, that means we have 2 numbers and 2 slots. Now if we look at number 1 first of all, then there's a 1 by 2 chance of going either into slot 1 or slot 2. Now why did I say 1 by 2? Because the problem states that there's an equal chance of going into any random slot. Well, that just means that each slot has the same probability, and since there's 2 slots, that just means that each slot has a 1 by 2 chance, right? Now if we look at the first case of this number 1 going into its correct corresponding slot, which has a probability of 1 by 2, well, if we start to write out the formula for e of 2, that's a 1 by 2 probability of the number of matches given we take this edge over here. Now what will happen if we take this edge? So number 1 goes into the correct slot, so that gives us 1 match. And then number 2 is, well, for this number, it's effectively the case of E of 1, right? Because there's just one slot and one number, right? And E of 2 has to go into this slot. So, well, we know the answer for this is also going to be 1, as in there's one more match. But try to look at this situation from the perspective of this being the case of E of 1, right? Since there's just one number and we also have its available corresponding slot, right? So the number of matches that are gonna come out from this situation is gonna be E of 1. So I'm gonna say E of 1 inside of this plus 1. E of 1 for this and 1 because we got one match, plus the other case where number 1 takes up this edge and basically number 1 is sent to slot 2. So now what's left is number 2 over here is forced to go into slot 1. So we see that 1 had to go into 2, which would not lead us to a match. And then number 2 was also forced to go into slot 1, which would also not lead us to a match. So this, for this case, for this edge, the number of matches is 0. So if we try to calculate this value of 1 by 2 of E of 1 plus 1, we get an answer of 1 again. So E of 2 is also equal to 1, right? We also know that E of 1 came out to be 1. Now let's look at the case of K is equal to 3. If you look at number 1 again, then there's a 1 by 3 chance of going into each of these 3 slots. Now let's try to start calculating the formula. Now again, there's a 1 by 3 chance of going into the correct slot, which will lead us to a match. And again, what happens is effectively we're left with E of 2, right? Again, try to look at this situation from the perspective of we have two numbers and their correct corresponding slots remaining, which is effectively just the beginning case for E of 2. So there's a 1 by 3 chance of taking this edge times the expected number of matches that we get using this edge, which is 1, right? Because 1 goes into the correct spot, plus the expected number of matches we'll get for E of 2. And over here, you're starting to see why recursion is used, right? But let's go on for now. Plus, now there's also these two edges that could happen, right? And both of these edges have a chance of 1 by 3 each. Now, both of these edges are going to be somewhat symmetrical. So let me just take the case of 1 going into slot number 2. Now, since this leads to 0 matches, and now number 2 in itself has two options. Either it could go to slot 1 or slot 3. So what's happening is, again, we have two cases. Now this has a probability of 1 by 2 and this arrow also has a probability of 1 by 2. If 2 goes along this edge, then so 1 effectively went into this edge, 2 went into slot number 1. Now 3 is left with its own corresponding slot. So this is effectively E of 1, right? So what happened was there was a 1 by 3 of chance of going here. And since it's also the same for this edge, we'll just say 2 by 3, right, for now. Inside of these two edges, for 2, there was a 1 by 2 chance of taking up this edge, which would lead us to 0 plus E of 1, but this was also 1 by 2, plus a 1 by 2 chance of 2 taking up this edge. Now what happens when 2 takes up this edge? 3, well, 1 is over here, 2 goes over here, and there's no number over here, so 3 has to take up this slot, which would not lead us to any edge. So this is 1 by 2 of 0. So this is effectively the equation that's coming out for the case of E of 3, right? To write it down again, this is what we came up with. Well, let me just explain this again real quick. We had three numbers, 1, 2, and 3, and 3 slots, right? For this number 1, there was a 1 by 3 chance of creating a match and a 2 by 3 chance of not creating a match, right? Which is denoted by 1 by 3 and 2 by 3 over here. For the 1 by 3 edge, this one, we get a match first of all, which is denoted by this one. And then we effectively have the case of E of 2, which is denoted over here. And this completes the case of 1 by 3. For the 2 by 3 cases, right, these cases over here, since both of them are symmetrical, I just talked about the case of this edge. So what happens in this edge is 1 effectively takes up this spot, and now 2 has two options of either going this way or this way. This is denoted by the 1 by 2s. And then what happens is, so if 2 takes up this edge, basically it takes up 1's edge, which was in turn taking up 2's slot. Now if this happens, we're again basically left with E of n minus 2 or E of 1 in this case, because what happens was 1 took up the slot of 2 but 2 took up the slot of 1, so they both cancel each other out and we effectively left with E of n minus 2 or E of 1 in this case. So this was denoted over here. And there was also 1 by 2 chance of 2 taking up this slot. In this case, 3 has to take up 1 because that's the only one left. And there's no matches at all. So this is denoted by 0. So if we calculate this value over here, this also comes out to be equals to 1, right? Now let's try to look at the general case of E of n minus 1 and E of n, because we're already starting to get a feel for recursion. Now for the general case of, let's say, k is equal to n, we have n numbers and n slots, right? Now Now, talking about the first guy, there's a 1 by n chance since there's n slots over here, and the correct one is only one among them. So there's a 1 by n chance of taking up the correct slot, in which case there's a match for this guy over here, and it's effectively the case of e of n minus 1. So as usual, the first case becomes a 1 by n chance of 1 plus e of n minus 1, and we're left with the n minus 1 over n other edges, right? Now for these cases, since all of them are symmetrical, let's just take up this case. Now, if one takes up number two, now there's n minus 1 remaining slots, and each of them are of, again, equal probability. Now, again, there's in a way only two cases. Either this edge goes somewhere here, or we take an edge that goes here. Well, if we take up this edge, which again has a probability of 1 over n minus 1, since out of these n minus 1 remaining edges, we take up one of them. And what happens in this case is effectively where we get the case of e of n minus 2, right? And there's also these other cases which have a probability of n minus 2 over n minus 1, which denotes choosing any of these n minus 2 edges over all of these n minus 1 possible edges. So let's say we take up this edge. Now what happens is, again, there's no match, right? Because this is not a match. Now again, for this guy, there's n minus 2 remaining slots, and either you could take up this one or you can take up any of the edges that go this way. So again, the equation over here is going to look something like the probability of taking up the leftward edge, right? This guy denotes this edge. So that's only 1 over all the n minus 2 possible edges. And in that case, you will end up with n minus 3, the case of n minus 3, because these three cancel out each other, and there's just n minus 3 to consider. But there's also the chance of we don't take up that edge, which is n minus 3 over n minus 2, because there's going to be n minus 3 edges over here over all of the n minus 2 remaining edges. And in that case, again, the recursion goes deeper and deeper. And if we simplify this formula over here, we see the recursive nature of this formula. So effectively what's happening is e of n is equal to 1 by n, 1 plus e of n minus 1, plus n minus 1 upon n, 1 upon n minus 1, e of n minus 2, plus n minus 2 upon n minus 1, and it keeps on going on. So here, this is what we're looking at. Now, if we look closely, this value over here is very similar to e of n minus 1. Now, if I were to use the exact same formula and try to write e of n minus 1, it would look like this. So all I've done over here is I took this entire equation over here and plugged in n minus 1 wherever I found n, right? And I get the value of e of n minus 1. Now, if we look at this part over here and this entire equation over here, we can figure out that e of n was effectively just, but first of all, it was this part. So this plus n minus 1 upon n times. Now try to substitute this part for e of n minus 1. We can see that if we use e of n minus 1 minus 1 upon n minus 1, so basically we're taking this sum over here, the remaining part is exactly the same as what's over here. So effectively I could say that this comes over here. Now, and this part is basically this over here, right? So e of n minus 1 minus 1 upon n minus 1. Now this becomes a recursive equation. Now, if we solve this, which is pretty simple, we get the value of e of n is equal to e of n minus 1, which is what we somewhat started to expect because each value is coming out to be equal to 1. So yeah, now if e of 1 is equal to 1, then that would mean that e of 2 is equals to 1. And that would also mean that every single value, e of n, any value of n is also equal to 1. So 1 is the answer to the problem. So that's one way to solve it using recursion, the way I found out initially. But there's also another way to solve this, and this is very similar to the Brainstellar solution, but we're going to look at it from a different perspective. So we've already defined what a match is, right? So if the ith number matches, that just means that the ith letter went into the ith envelope, or the ith number went into the ith slot, right? Now, what we've been asked in the question is for a random arrangement of these n values, what is the expected number of matches? Right. Well, for calculating this, let's first look at a very useful observation. What is the probability that the ith number matches? Now, since we have n letters and n envelopes, and each of for each of these letters, the probability of going into any one of these envelopes is random and equal, well, I could say that the probability of going into any one of these letters is 1 by n, which means that the probability of this guy going into its corresponding envelope is 1 by n, right? And this is exactly what is the probability of the ith letter matching, right? Since no matter what happens, from the perspective of this guy, all of these letters, right, this letter, sorry, these envelopes or these slots are completely equal and identical. By symmetry, we can say that the probability of this guy going into its corresponding match is going to be the same as the probability of this guy going into this corresponding match or this guy. So basically, it doesn't even matter if this was the first guy to be sent into an envelope. So the usual problem with this answer for guys is that, well, this is because you pick the third guy to be sent into one of these slots first of all, right? What if the first and the second guy were first of all sent to their respective slots, and then this third guy was chosen to be sent into a respective slot? Well, it doesn't matter, because no matter what you do, from the perspective of the entire system, this letter has no bias towards any one of these slots. So by symmetry itself, the probability that it's going to end up in one of these slots is going to be equal always, right? So that's why we can say that the probability that the third or the ith letter matches with its corresponding slot is going to be 1 over n. So if we've established that the probability of the ith match or the ith letter matching is equals to 1 by n, now we just need to calculate the value of expected number of matches. Now, how do we connect these two values? And this is the problem where we need to introduce indicator variables. So now let me just show you the Brainstellar solution so that we can talk about those variables. So here we are. For every Brainstellar solution, they straight away start with defining these variables, but I find that somewhat non-intuitive. And I'm trying to give you guys the reason why they define these variables. So over here, they've defined xi be equals to 1 if there is a match or 0 otherwise. Now, all these variables do is help to connect this value, the probability of the ith matching, to be able to be used while calculating the expected number of matches. Because all we're going to do is now is going to say that the expected number of matches is going to be the expected number of sigma xi, right? Because sigma xi, well, each xi is basically 1 whenever ith guy does a match, and the sigma of xi is just going to denote the total number of matches that happen for a random arrangement. And if we calculate the expected value of that, we get what we wanted, right? So it's pretty easy to see how these variables help us calculate this value, but it's tough to understand why they define this initially if you don't have this background already. So yeah, so if we define these xi variables, then, well, we already now know that the probability of each of any of these xi being equal to 1 is basically the probability of an ith match is equal to 1 over n, and the value that we're trying to calculate is the expected number of total matches, which is basically the summation of all of those xi values, which basically comes out to be sigma e of xi, and each e of xi will just be p of xi is equals to 1 into 1, which will come out to be 1 by n. And since the sigma goes from 1 to n, we basically get the value of 1 as shown over here. So for quite a few problems on the website, the way the Brainstellar solution approaches the solution is by directly defining these indicator variables. And the entire point of these variables is to try to connect what we want to calculate eventually, which is the expected value of something, to a probability that we already know about. And the variables defined are usually of the pattern, let's say xi is equals to 1 for what we want being satisfied for any ith value, and xi is equal to 0 if what we wanted is not satisfied for that ith value, right? It's something like that. The entire point of these is to try to calculate or make it easier, or try to assign numerical values of 1 and 0 to the event happening for any ith guy. Now, what I've tried to done in this solution is to first of all give you the idea of the underlying probability. That was pretty simple, and how that probability is going to be connected to the eventual value that we're needing is how we come up with these xi variables. So what we've done is first focus on the underlying property, right? So over here the property was count the number of expected matches, count the number of matches, right? And this underlying property is of what the expected value we need to calculate, right? So we first focus on the underlying property, and we calculate the probability that the counter is going to increase each position I. which led us to the probability of the ith guy matching, right? And then to connect P of ith guy matching and the expected number of total matches, we introduced this indicator variable. I hope you guys understood both of these solutions, and thanks for watching.